Final chapter we're going to get into in Pre-Calc 12 is Chapter 3. Chapter 3 has to do with polynomial functions. We've seen polynomial functions. You've seen them for a number of years, but these are just basically all polynomial functions. Okay, so our last one here, let's see, the polynomial function is one of the form. Now I'm going to write it like this. F of x, or in other words y, whatever you want to call it, is a sub n x to the power of n plus a sub n minus 1, x to the power of n minus 1, plus blah, 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 all the way down to a sub 1 of x to the power of 1 plus a sub 0. Now, these are all just coefficients, right? So n is going to be a whole number. In fact, a whole number, it has to be positive, right? It's well, it could be 0. That's kind of pointless. But 1, 2, 3, blah blah blah. So we're not talking about n to the power of -1. No, no, no. X to the power that would be a rational function. That'd be a fraction. So we're not doing those. Nice. So we know that the highest power is going to be n. X is a variable. Okay, we know that. Variable. And a sub n all the way to a sub 0. These are real coefficients. So they are real number coefficients. So they are numbers. Here's the first one you saw. Y equals mx plus b. So really, the b is the a naught, or a sub 0. And a sub 1 was this. So this was a line, right? And then you got into y is equal to, now instead of using m, we went a x squared plus bx plus c. Oh yeah, this is a quadratic, but a, b, and c are basically your letters in the same way m and b. Now, what if this thing is degree, I don't know, 400? Okay, well there isn't 400 letters. So that's why we're going to call it a sub n minus 1. So these are all just your coefficients. Okay, the leading coefficient, in other words, a sub n, it's the coefficient of the highest degree term, right? So it is the coefficient of highest degree. Highest degree term. So yeah, we usually put them in descending powers. You want to put the highest ones, the x squared, you put those ones first. Yeah, where the degree is going to be n. So in other words, it's the highest exponent. Well, the reason we do that is because if you're looking at a line or something like that, the slope is the important thing. Or if you're looking at a quadratic, right, this first one is going to tell you an awful lot. So like the higher the power, really the more influence this this coefficient has on how this thing behaves. Okay, so we've seen polynomials before. Remember, y is equal to 2x plus 3. It's a line, right? So that's called linear. I won't bother putting that in brackets. Boop. We know that this is linear. It's a line. Or you could have a y is equal to negative 2x squared plus 1. We know that that's a quadratic. Okay, we've seen these before. These things are polynomials. Or it could be y. Let's not use y. Let's use f of x. Same thing. Function of x is equal to 4x cubed. Okay, plus 3. I don't know, whatever. This one would be a cubic. Now, it's got a curve, kind of like a quadratic, but not necessarily. And then, yeah, you could see anything you want, like x plus 1 cubed, x minus 3. This one would be called a quartic. So degree 4, right? 1, 2, 3. Oh yeah, and there's a 1 there, right? Remember, if you were to expand this all out, it would start with like x to the power of 4. So what are not polynomials? Absolute values. Yeah, because this thing behaves differently, and remember, this thing kind of looks like this, right? It's got a kink in it. Oh yeah, it's got a kink right at the center. So that's not an absolute value because this thing's going to randomly change, well, at one single point. Y is equal to square root of x, because that's x to the power of a half. And remember, this is not a whole number, right? That's a fraction. That's a rational number. So when you get into radicals, yeah, we're not doing those in this chapter. In the same way, x times y is equal to 6. That's like saying y is equal to 6 over x, or in other words, 6x to the power of negative 1, right? This needs to be a whole number, and that is not. That is a negative number. It's an integer, so which means it's not a polynomial. So the nice thing we know about polynomials, if we remember from calculus stuff, These things are always going to be defined because they don't have a denominator. So they're always defined. They're always smooth and continuous. There's no breaks, there's no kinks, there's no nothing. So polynomials are really nice functions. They're well behaved. We like them. Okay, so we're going to be considering the end behavior of the polynomial. So in other words, in the book, they're going to call it the left-hand side or on the right-hand side, or they might say it goes up in quadrant 1 or up in quadrant 2 or 3. In other words, we know that this means the limit as x approaches infinity. It's okay to use this notation. We know what this means. So that means off to the right-hand behavior, or this could be the limit as x approaches negative infinity. They're not going to use this kind of notation in the back of the book because remember, you don't know anything about calculus. You don't know anything about limit theory. However, yes, we do. So if we want to use this notation, this is completely okay, right? So let's say you have, I don't know, some function that looks like this, and it's going to be continuous, and it's, boop, looks like that. Okay, so the way they would describe this in the back of the book, they would say the right-hand behavior, so right-hand side, goes to positive infinity. We could just simply say, remember, limit, or they would say it goes up, right? We can say limit as x goes to infinity equals infinity. We know what that means. And in fact, we should be using that. And the same thing for this. We would also say the limit as x approaches negative infinity is, hang on, is that positive or negative infinity? It's going up. That's positive. So careful. This is positive infinity. Negative infinity would means it's going down. But just beware of that. In the book, they're going to talk about the left-hand side or the left-hand side. They would say it goes down. No. In this case, it would also be up. Oh, yeah. This one is going to be, I don't know what the degree is, but another way of saying this, they might say it extends upwards in quadrants 1 and quadrant 2 without talking about quadrant 3 or 4. Okay, so yeah, we can use this notation because we know what it means. It's a smarter way to do it. Okay, so let's look at some patterns. So a degree 0 polynomial, for example, y is equal to 3, right? Y is equal to 3 is a degree 0 polynomial. That is simply a constant flat line. So yeah, so if I had y equals 3, this is like saying degree 0. This is like saying y is equal to, well, 3x to the power of 0. We don't really need to write it like that, right? Y is equal to 3. We know that that's called a constant. Yeah, a constant is a flat horizontal line, right? This is linear, but this is a constant. The end behavior, okay, so as you go limit to infinity and negative infinity, so in other words, the limit as x approaches plus or minus infinity. Let's get rid of this. Limit as x approaches plus or minus infinity, in this case, is 3, because it's just constant. It's just always 3, right? The y value is 3 off to the right, the y value is 3 off to the left. So how many x-intercepts does this one have? It has 0. It has none. Well, other than if you had a flat horizontal line right on the x-axis, but that would be every single point, which would kind of be pointless. Okay, let's see one that's degree 1. Remember, y equals 2x plus 1. Oh, in other words, the highest power is x to the power of 1, right? We call these linear. Yeah. Now, y equals mx plus b. This would be a sub 1. This would be a sub 0. So the end behavior, you could say it's up in quadrant 1, and you could say it's down in quadrant 3. That's typically how they're going to write it in the back of the book. If you want to say the limit as x approaches infinity is infinity and the limit as x approaches negative, yes, you are completely right. Please do it. How many x-intercepts does this thing have? It has 1. Exactly 1. Only 1. Period. It has 1 and it's degree 1. What about a degree 2? Remember, we call these quadratics. We know these. Okay, a quadratic, I remember these. Remember the quadratic formula. The quadratic formula is just for these 2 points, right? This would be the number of x-intercepts. This thing could have 2, or it could have 1, right? If we were to move this whole thing up 3, or it could also have 0. Remember, sometimes there is no answer to a quadratic. So the number of x-intercepts is 2 or less. And the end behavior, I'm going to say it's up in quadrant 1 and quadrant 2. Okay? It's going upwards. It's going up to positive infinity. That's the end behavior. So the left hand and the right hand sides. Okay. Let's get to this one. So y is equal to x cubed, 2x squared. Basically, this thing is going to be a cubic. Now, there's lots of different shapes of cubics. If I was to get rid of all these things, the simple shape of a cubic is something like that, where one side's going up and one side's going down. But that's not what happens. As soon as you bring in these other terms, they start to change this shape, okay? So there's no simple shape that it always is. Like lines, there's a simple shape. Parabolas, there's a simple shape. This thing, no, it depends. So it kind of depends upon the other terms. However, the x cubed is the most important one. So the end behavior of this thing, okay, so let's say the limit x goes to infinity is infinity, and the limit x goes to negative infinity is going to be negative infinity. In other words, that means it's going down and up. Okay, we know that. The number of x-intercepts, this one has 1, 2, 3. It could also have 2. If I was to decide to move this one down, 1, 2, it could have 2. It could also have 1. Let's take this whole thing and move it all down. So it's going to be crossing 1. Could also have 0, right? No, that's not possible. Why not? Here's why. Because one side goes down to infinity and one side goes up to infinity, and because these are polynomials are always continuous, they're always smooth, there's no breaks, there's no nothing. This thing, sooner or later, has to cross the x-axis. So that's not a possibility. Oh yeah, just like a diagonal line has to cross the x-axis. The only time it wouldn't is if it was a flat horizontal, which is a different kind of function. Okay, so a cubic, basically the cubic's telling you that the number of x-intercepts, the degree is 3. It could be 3 or 2 or 1, but not 0. Okay, degree 4 is called a quartic, just for some weird name. This one has 1, 2, 3, 4. Yeah, so the end behavior, let's say limit x approaches plus or minus infinity. In this case, it's positive infinity. How can I tell? Well, look at the graph, but also the leading coefficient. If this thing's positive, you remember, it's going to go to positive infinity. Oh yeah, both sides. Why? Because it's an even degree. Oh yeah, odd, even. Odd are in opposite directions. Even's going to be the same. So be it here, or an even like a quadratic, see, they're the same direction. Okay, that's kind of useful. So the number of x-intercepts, it could be 1, 2, 3. It could be 4 or 3 or 2 or 1, or it is possible to be 0, right? Let's think about this. If you had like x to the power of 4 is equal to negative 4. Yeah, you cannot do an even powered root of a negative, right? That's never going to happen. So that's why you could get 0. Okay, what about this last one? This one's called a quintic. Quintic, like anyone really cares. And this one has 1, 2, 3, 4. So really the degree of the polynomial means the number of x-intercepts it could have. It could have 5 or 4 or 3 or 2 or 1. Could it have 0? No. Because one side goes up to infinity, one side goes down to infinity. It has to be continuous because it's got no denominator. And yeah, the end behavior in this, let's say it's up in quadrant 1 and it's down in quadrant 3, right? 1, 2, 3. It goes down to infinity. Okay, so they're going to ask you about end behavior and stuff like that. And really the x-intercepts, those are solutions to equations, right? Whenever the function equals 0. So if I said this whole thing equal to 0, I'd be solving an equation, right? When I get rid of the y equals, it just becomes these answers. So it really tells you you could get up to 5 answers. If it was a quartic, you could get up to 4 answers, maybe no answers, right? So the right end behavior is determined by the sign of the leading coefficient. Positive, positive, positive. These are all positive. So the right-hand side always goes up to positive infinity. So in this case, I should say that the right-hand behavior is determined by the sign of the leading coefficient. Leading coefficient. Right? So that's why we put the highest powered one first. We also might notice that the y-intercept is really the y-intercept. Remember, way back to when? Y is equal to mx plus b, this number on the end, that's the y-intercept, it's 1. Oh, look at this. Blah, 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 blah. Number on the end, -3. The constant on the end. Oh, that's right. Some kind of weird thing. -2 is the constant on the end. There it is, -2. So, oh, yeah, because if I set in the x values of 0, right, all of these x's disappear, and the only thing that sticks around is the constant on the, in other words, a sub 0. That's the y-intercept. The y-intercept is simply the constant term of the polynomial. So it's really a sub 0. So the number on the end is always the y-intercept, not the x-intercept. It's the y-intercept. The x-intercepts may vary. So the number of turning points, well, we know that they are local min or max, right? Oh, remember critical points? Now, the book doesn't know. I know that's a critical point. That's a critical point. They refer to these as turning points. It's a place where it turns around. Way back when, we called it the vertex of the parabola because there's only one, right? However, for a cubic, I wouldn't call this the vertex and this the vertex. Those are turning points. We know that they are critical points. The book is not going to be using critical points. They will call them turning points, but we know that they are critical points. This is where the derivative is 0 or undefined. Psst, it's always defined, which means it's always going to be 0, right? At those. And if you want to define those critical points by doing a derivative, by all means, feel free. However, the book is not going to ask you to do that. And I won't ask you to do that in this last chapter. We don't even remember what derivatives are. I just want to look at the behaviors of these things. And it may be one less than the degree. So for example, the degree 2 can only have one critical point. Or degree 3, it might have 2 or it might have 1, right? So hang on, let's take a look at this thing. Match each function with the corresponding graph. Well, let's see. This one is g of x. What do I know? I know it's going to be negative, so it goes down to infinity. No. Maybe. No. Maybe. Okay. This thing is degree 4. This thing has 1, 2, 3, 4 critical points or 4 turning points, which means it's got to be at least degree 5. So g is going to have to be, this one has 1, 2, 3, 3 turning points. So this one is g of x. It's going down to infinity. That's the negative right here, right? That's the leading coefficient. I know that the leading coefficient is going to tell me it goes down to infinity on the right-hand side. It's an even, which means they're going in the same direction. Oh yeah, see, this goes down to infinity, this goes down to infinity. Okay. Let's do the x cubed. It's positive, +1. So it's going to be the right-hand side goes up to infinity, maybe, maybe, no, this one goes down. And it's degree 3, which means this thing will have maximum 2 turning points. This one has 1, 2, 3 critical points. No good. This one has 1, 2. There it is. So this one's going to be f of x. How do I know that? Well, a couple of things. I looked at positive means the right-hand side goes up to infinity, and this thing is degree 3, which means that I can only have 2 maximum points. Okay. Negative degree 5. It's got to be this one, because this one's got 1, 2, 3, 4 turning points, so 4 critical points, and it's going in the negative direction. So notice I'm not looking at the left-hand side. I'm only looking at the right-hand side. Why? Well, because the right-hand side is going to be determined by this negative. So yeah, this one's going to be p of x. What about the left-hand side? Well, it depends. It might be opposite or it might be the same. See? In this case, because it's an even, they go in the same direction. But this one's an odd, which means they go in opposite direction. Oh yeah, degree 3. And this one is, got to be the last one. It's positive, going up to positive infinity. And it's degree 4, which means they're in the same direction. And this one has 1, 2, 3 turning points, or 3 critical points, which means h of x. This one must be, it's got to be at least degree 4. Okay. So because odd degree polynomials have the opposite end behavior, opposite, we are guaranteed the existence of at least one x-intercept. So in other words, there has to be at least one solution if it's an odd degree polynomial. So for example, x cubed is equal to who cares? I know there's always an answer, right? There has to be. But if I had x squared is equal to -4, right? There is no answer. That's impossible. So that's why odd degree polynomials always have at least one x-intercept. They always have at least one answer. And because even degree polynomials have the same end behavior, you are guaranteed the existence of an absolute min or max. What? Oh, that's right. So they might still ask you about the minimum and maximum based upon the shape of the graph. Degree 5, this thing goes up to infinity and it goes down to infinity, which means the range is going to be all real numbers, right? There is no absolute maximum or minimum. However, with something like a polynomial or degree 4, for example, this one's degree 4, here's the maximum height that it goes up to. This looks like it's 40. This is probably like, I don't know, 36 or something like that. There is the absolute maximum, and you could say it's always below this point. So the range, in this case, y values would be less than or equal to 30. I'm assuming it's 36. 1, 2, 3. I'm not going to count them. So it's not going to be all real numbers. So the range in this case would be up and down to infinity. No. This one, it is restricted. So there is an absolute maximum, or there could be an absolute minimum. Like this one, degree 4. There's the absolute minimum value it goes down to, never goes below. So because of that, I can say that there is an absolute minimum or maximum. Okay. Our first section to look at, and yes, you can plug these into a calculator and look at them, but also it's also faster just to think about, okay, should my end behavior be the same or opposite? And is it going up or is it going down? How do I know? I'm looking at that first coefficient, the leading coefficient. Alrighty, good luck with these.